Alright, so today we're going to continue with our unit on applications of aqueous equilibria. We're going to look at titrations and pH curves. So you may remember titrations from chapter 4. Excuse me. We did one with the Tums, the antacid, to see how much base it would take to neutralize the acid in your stomach using an antacid. So titrations are used to determine the amount of acid or base in a solution. So we take a known concentration, which is the titrant, from a burette, which was that long glass piece of equipment, and we titrate it into an unknown solution. So the equivalence point is signaled by a color change of an indicator. Ours, I believe, went from clear to purple. There are lots of different indicators, and we'll talk about these in the next section. And we can also plot what's called a pH curve or a titration curve, and it's basically a plot of pH as a function of the amount of titrant added, and so we'll look at some of those also. Before we move on, because we're working in small quantities, it's also going to be convenient to talk about, instead of the mole, the millimole, which is basically, like a milliliter is 1/1000th of a liter, it's 1/1000th of a mole. And so molarity can be represented as moles per liter or millimole per milliliter. There are three types of titrations that we're going to look at. First one is strong acid, strong base. Then we're going to look at a weak acid with a strong base, and then we're going to look at a weak base with a strong acid. And we'll also talk about how to calculate Ka in there also. Okay, so first of all, we're going to look at a strong acid, strong base titration. So we know that strong acids and strong bases completely dissociate, and so that gives us a net ionic reaction of just the H plus the OH minus producing water. So let's say that we have 50 milliliters of a 0.2 molar nitric acid with 0.1 molar sodium hydroxide. So strong acid, strong base. We're going to go through this in steps, looking at what happens to the pH as we add more NaOH, and we're always adding it to the original solution. So in this case, we could take those points and plot them and get our pH curve. Okay, so first of all, if we just have our nitric acid, it's a strong acid, so we know it's going to completely dissociate. So that gives us our major species of H+, the NO3-, and then also water. And so in this case, this is a regular pH problem. Our pH is going to be determined from the H+ concentration. Well, we know that the concentration of the acid is 0.2 molar, and because it completely dissociates and it's 1:1, that means that the concentration of the H+ is 0.2 molar, and we could do negative log of that, giving us a pH of 0.699. Very acidic. That makes sense. Okay, so now we're going to start titrating. We're going to start adding small quantities of the NaOH. And so first we're going to add 10 milliliters. So before the reaction, we have the two parts of our acid. Okay, we know, whoops, I'm in a pin. We know that we have the H+ and the NO3-. We know this base is strong, so it dissociates, and then we have water. Okay, also notice that we have large quantities of the H+ and the OH- present. So we talked about how before that these types of problems we're going to just dissociate into the H+ and the OH going to just water. So if we look at before the reaction, we had 50 milliliters of a 0.2 molar nitric acid solution. So if we want to find the number of moles or millimoles, since it's in milliliters, we just multiply. So we had our 50 milliliters times we had a 0.2 molar solution, and that gives us 10 millimoles of the H+. Okay, if we look at the OH-, we have our 10 milliliters of a 0.1 molar solution. So when we multiply those together, we get 1 millimole. Oh well. Okay, then if we look at after the reaction, well, we know that all the OH is going to react with the H+. So we're going to subtract 1 millimole from here. We're going to also subtract 1 millimole from here, and we would add it over here, but remember, water, we're not really considering it. And so if we look at what happens after the react, we're left with 9 millimoles of H+ and no millimoles of the OH-. kind of, sorry about that. So if we look at after the reaction, okay, we don't have any OH left because we consumed it all. So we just have our H+, our NO3-, our Na+, and our water. So we're going to determine the pH from the remaining H+ after the NaOH has reacted with the HNO3. And so in order to do this, we take the millimoles that are left, okay, because that's the remaining H+, and we divide by the total volume of the solution. Now, because we're working in millimoles, we could do milliliters, and so we know we have 9 millimoles of H+ left after the OH reacts. And now we want to look at the total volume of solution. Well, we had 50 milliliters from the nitric acid, and we had 10 milliliters from the sodium hydroxide. So that gives us 60 milliliters total. Now we could convert to liters and do moles, but this is so much easier, and they're both base of 1,000, so it works out to be the same. So this gives us 0.15 molar for our concentration of H+, and then we can use that to determine our pH. And so our pH is negative log of that 0.15, which gives us 0.82. So we went from, what, about a 0.7 pH to a 0.82 pH, which makes sense. We added a little bit of base. We're reacting the H+ with the OH. We're moving our pH up. Okay, so now instead of adding 10 milliliters, let's add 20 milliliters instead. We're always going back to that original solution. This is the same idea as the previous situation, same type of calculation. So the OH- and the H+ are going to react to form water. And so we have our H+ plus our OH-, and I'll try not to write too big so it doesn't write over the text from below. So first we want to look at our before reaction. This is going to be very similar to what we had in the other example. So we know that we already had 10 millimoles of the H+. However, OH- is a little bit different. We have 20 times the 0.1, and so that gives us 2 millimoles now instead of the 1 millimole from the 10 milliliters that we did previously. You know, we're not counting water. So we're going to subtract, now all that OH is going to react, so we're going to subtract the 2 millimoles this time. And so our after reaction is 8 millimoles of H+, no moles of the OH-, and we're not including water. So now we're going to use that to figure out the concentration of the H+ that's left. So just like we did before, we take the millimoles of H+ left, that came from here. We divide it by the total volume of solution. In this case, we had 50 of the nitric acid, and now we have 20 milliliters of the sodium hydroxide, and that gives us 0.11 molar, and then we can use that to determine our pH by taking the negative log, and we get 0.942. So it makes sense. Our pH is going up. Okay, now we're going to add 50 milliliters of 0.1 molar NaOH. This is very identical to the other two calculations that we did. So we're starting with 0, we keep adding NaOH. Eventually we're going to get to what's called an equivalence point, and I think that's coming up next. But just, we keep going with this same type of calculation. So if you do all of that, and you could go ahead and pause and do all that calculation on your own, make sure you get this pH of 1.3. Okay, but our pH is coming up as we're adding base. Okay, so now we're getting to a point where we're adding 100 milliliters. So our amount of NaOH is 10 millimoles because we take our volume times our molarity. Well, this is identical to the amount of nitric acid that we're starting with. And so this is what's called the equivalence or the stoichiometric point. Remember, stoichiometric point is where you have exactly enough of both where they'll react. You have nothing left over, no limiting reactant, nothing like that. Or maybe they're both limiting. So if we look at our major species, because the OH is all reacting with all the H+, we don't have any H+ left like we did in the previous ones. And so now our major species are the Na+, the NO3-, and then a whole lot of water. Well, Na+ doesn't contribute. It doesn't have any acid or base properties. NO3- is the anion of our strong acid, making it a weak base. So really, neither of these species are going to affect the pH at all. So that leaves water. Well, the pH of water is 7, and so this means that now the solution is considered neutral. So it's kind of interesting. We had very gradual pH changes, and then all of a sudden we jumped up to 7. Okay, so this is what's called the equivalence point, where we have equal amounts and our pH is neutral. Okay, now let's go past the equivalence point. Let's keep adding base. Well, where before we had an excess of H+, now because we're going past the equivalence point, I would assume we're going to have an excess of OH- instead. We still have the H+ reacting with the OH to form water. So let's look at that. We had our H+ and our OH-, and we're forming water. Now this is very similar to what we did in the previous problems. We're still starting with our 10 millimoles of the H+ because we had 50 milliliters of a 0.2 molar solution. Now we have 150 milliliters of a 0.1 molar NaOH, and so if we multiply that together, that gives us 15 millimoles. So now, this is our before reaction. So now we're going to react, but this time we have less H+. So we're subtracting the 10 millimoles here, we're subtracting it here because that's what's reacting. And so for our after reaction, we have no H+ left, but we have 5 millimoles of OH- left. And millimoles is really hard to write, that extra M. It's really getting me. Okay, so now we have an excess of OH, not H+. And so because it's an excess, it is going to determine the pH. And so we are going to find the concentration of the OH, just like we found the concentration of the H+ from before. So we take the number of millimoles that's left over, and we divide it by the total volume. So here we had 150 milliliters of the NaOH, and I believe we had 50 milliliters of our acid, so that makes 200 milliliters total. And so 5 divided by 200 is 0.025 molar NaOH. But we want it, or I guess OH-, right? Because the Na is really not there anymore. Okay, so that's our concentration of OH. Now we want to find the H+ concentration because we need to determine pH. Well, we know that Kw is equal to H+ times OH-. So if we just rearrange that equation, we get this. We know Kw is 1 × 10⁻⁴. We just found our concentration of OH-, and that gives us a concentration for H+, 4 × 10⁻⁻13. And then we can use that negative log of it to find the pH, and it's now equal to 12.4. So we went from a neutral, now we had excess OH, and we're at a pH of 12.4. So that's logical, that makes sense. Okay, now let's add even more NaOH. Let's add 200 milliliters instead of 150. Well, you're going to do very similar calculations to what we just did. And if you do all those, and you can go ahead and pause and try this on your own, you should get a pH of 12.6. So not too much of a change. Went from 12.4 to 12.6. So what hopefully you noticed is that the pH changed gradually until the titration got close to that equivalence point with that 50 milliliters, or I guess the 10 millimoles of the H+ and the OH-. And then it went to neutral. And so the reason that you have this small and then big change at the equivalence point is because we have this small amount of H+ and a small amount of OH-. And because we have a small amount of each, it's going to cause big changes. But when you have large quantities of one or the other, in addition, like a large quantity of H+, a small addition of OH- isn't going to change anything very much. And so that's why you're getting this big change at the equivalence point, or close to it. So before the equivalence point, the H+ was calculated by dividing the number of millimoles of H+ remaining by the total volume. At the equivalence point, we know the quantities are equal, so the pH is 7. And then after the equivalence point, same idea as before, but now we have excess OH instead of excess H+. And so we calculate our excess OH, then we get the H+ from the Kw, and then calculate our pH from there. Okay, so if we look at these pH curves, what we could do is plot those pH points along as we added volumes of NaOH. And if you see from, we either have a strong acid, or let's say we titrated with a strong base and used HCl. The curves are pretty similar, they're almost mirror images. And you can see that the equivalence point is at 7 for both of them. And so it really doesn't matter which way you go, if they're both strong, we're going to eventually get to that equivalence point where it's 1 to 1, and we would have a pH of 7. Okay, so next we're going to talk about how we titrate with a weak acid and a strong base.